know. So the first reaction was the addition of hydrogen. The addition of hydrogen is seen as a hydrogenation, and you just ended up with, of course, the alkane, which was 2-methylpentane. The next reaction was a hydrohalogenation, which follows Markovnikov. So you end up with only one product, where the chloro is on carbon 2, and so your product is 2-chloro, 2-methylpentane. And you can stop me and ask anytime. Okay, so if anything you need for me to clear, please do. For letter C, this is a non-Markovnikov hydrohalogenation, where you end up with the HBr and peroxides. The HBr and peroxides is a non-Markovnikov, and so your bromine went to carbon number 1, and so your product was 1-bromo, 2-methylpentane. Letter D is the total opposite. It's like exactly like B. It's called a hydrohalogenation. It's a Markovnikov hydrohalogenation, where the bromine actually goes on carbon 2. So, if you really want to have a 1-something, a 1-bromo, you need to have the double bond at the end of the chain or at the beginning, like in the 1 position, so you can get to that. For letter E, this is a simple hydration. A simple hydration was the sulfuric acid and water. Simple hydration is also a Markovnikov addition of water. And so that's what we end up having here. For letter F, that was again your BH3 in THF, which is a hydroboration oxidation. It's a non-Markovnikov addition of water. And you will have your OH and your hydrogen coming from the same side. If you're in an open chain, it doesn't show too well. It usually shows much better if you're in a ring that you can really highlight it better. Letter G, we're adding chlorine to the double bond. The addition of chlorine to a double bond is called a halogenation. It really adds in an anti-stereochemistry. I mean, that really should be the way that it should be drawn on the right-hand side. That is an anti-addition, but I sloppily wrote it like this, right? So you have the sloppy and the perfect. You choose whatever. I probably accept sloppy, sadly. It's plus an enantiomer. And she says plus an enantiomer. I guess so. So plus an enantiomer, thank you very much. Let's fix my notes here. Plus an enantiomer. Good job. So carbon 1 is achiral, but carbon 2 is chiral. So plus the enantiomer. So if you go like that, or if you go like this. So that's G. Everybody still with me? Everybody is caught up? We're all good? All right. I turn the H. H is the MCPBA. MCPBA is seen as an epoxidation. And you do put the triangle in a syn stereochemistry. It can be to the bottom, to the top, to the right, to the left. It doesn't really matter where that is going. But that is your epoxidation. And MCPBA is really this. I don't know if you saw the structure before. You don't have to know it yet. When we do aromatics, we'll bring it and then it'll all make sense. So for now, here it is, there it isn't. You don't need to know it. All right, we turn the paper over and we look at letter I. And letter I is the osmium tetroxide, which is a hydroxylation, osmium tetroxide, OSO. Second Spanish word of the day, OSO, is now there. Now you have 2 Spanish words, okay? So osmium tetroxide, OSO4. All right, OSO4 does a syn addition of a diol. And you end up with that, and of course, I think you can say the enantiomer too, since that carbon number 2 is chiral, so that and the enantiomer. Or we can go ahead and go the easy way out and call it R and S. Much easier than write the whole enantiomer word thing. I look at J, and when I look at J, I think we had a little bit of a difficulty because the easiest way to do J, which is an oxidative cleavage, is to make sure that you go ahead and you put your hydrogens, right? So I'm putting my hydrogens right here so you can see what happens if you put your hydrogens at that end. When you're cleaving, it's like you're going, excuse me, may I cut in? And you're just doing is separating that double bond and putting oxygens in its places. So if you were under mild oxidative conditions, ozone is mild. Mild, you keep your hydrogens. Stronger, it goes all the way to the CO2. So I know that some of you, even from Dr. Arnaiz, do as a CO2, but that is under harsher conditions. Stronger, which is the stronger, bless you. The stronger oxidative conditions is permanganate and heat. Ozone is mild. It's the only way to make aldehydes with cleavage. All right, the only way to make aldehydes upon cleavage, cleaving is taking a double bond with ozone. Anything else is much harsher and will go to a carboxylic acid or CO2. Because there are 2 carbons at that end, that's where you get the ketone. So 2 carbons, that was the ketone. The other 2 sides, the 2 hydrogens. So you leave things the same the way they were at the beginning. So your alkene, the way it was, all you're doing is, excuse me, let's go ahead, spread out, put oxygens on either end. All right, and everything remains the same. So an aldehyde and a ketone in this guy. For letter K, that's that oxymercuration, demercuration that we talked about. At that moment, you just have the Markovnikov alcohol, and so there it is. That's your Markovnikov alcohol right there. Your OH is in that place. For letter L, that was carbene chemistry. So LMNO. See, I was doing these tests before the band came along. So before they came along, that what is it? LMFAO, whatever their names are. I had my LMNO before they did. So my LMNO is my carbene chemistry. This is where LMN. LMNO. All of those are carbene chemistry. People are going like, what? Your joke is not good. All right, so they're there. Formation of the ring. The best one is diazomethane. So for letter L, that is the best. Diazomethane, that will be the product. Does everybody see how I did it? From the double bond, you use the double bond, and there's your little triangle.
Does it matter if you draw the triangle?
No, you can draw the triangle up or down. Mine is looking kind of funky because it's going down, but it doesn't matter which way you draw the triangle. By far, the diazomethane, CH2, M2, the diazomethane is the best way of making carbene. It is explosive, it is toxic, we can't buy it, it's only on paper that we play this way. In real life, we just can't do it. Okay, the other one, which is letter M, is the Simmons-Smith. That's the way that we really can do it in the lab with the CH2I2 and zinc and copper chloride. You know, that's the Simmons-Smith. Again, this is total review today. What am I doing? And so N and O look like that. I doubt LMNO, none of this will be in this semester's work. So this one's I'm going through so fast because this is not applicable for like anything. All the other reactions may be needed for some more chemistry, but these guys, this is just like a blur. Just for today, just for the quiz, a week from today. 2 weeks from today. 2 weeks from today. Okay, and then letters P, are the hydroxylation cold. So this is your hydroxylation cold. Cold, again, you're doing the diol. So you're doing the diol with cold, and that's what you're going to have there. The two OHs coming from the same side. Plus the enantiomer, yes, plus the enantiomer again on that one. Yeah, the one to the bottom and to the top. Plus your enantiomer. And then the very last one where you're going to go ahead and you're going to cleave it. And when you're cleaving it, alright, when you're cleaving permanganate hot, what happens is, when you're under strong conditions, this is the first thing that happens, just like we did with ozone. So the first thing that happens is you get to the formaldehyde. The problem is that if you're under really strong conditions, you can't stop the oxidation of formaldehyde. Formaldehyde goes to the carboxylic acid. You can't stop, it goes all the way to CO2. So there's no stopping it. It's like you can't stop it. It continues on, continues on. If you have a ketone, the ketone cannot be oxidized any further. So it just cannot be oxidized any further. You stop right there. But your aldehydes continue on to a carboxylic acid, and if that other side has the hydrogen, that's why it goes to the CO2. This one is kind of like an important reaction. So let's try this one. So what happens if you have this one and you're oxidizing with permanganate and hot? Permanganate hot, what happens here?
Two ketones.
You don't get a CO2.
You don't get CO2. Right? Is everybody there? You don't get CO2. The only way to get CO2, you have to be a terminal alkene. Right? It has to be a one somebody. A one pentene, a one hexene. Otherwise, you don't get CO2. If you have an internal alkene, right? If you get an internal alkene and you're looking at your hydrogens, right? So remember, go ahead and put your hydrogens to guide you. If you put your hydrogens to guide you, again, that first step is that you go, choo, you cleave. Right, and from there, you will have that. There's one O and a hydrogen, and over here, you also have a hydrogen and the rest of the molecule, right, like that. That's the first step. We can't stop. It just doesn't stop. So this continues on, and now you go all the way to the carboxylic acid here, and the same at the spot. Right, so you just go to the carboxylic acid. All right, so in both cases, it's just the carboxylic acid. So the only way for you to have CO2 is if you have a terminal alkene. Okay, otherwise, CO2 will not be formed. And it only works with potassium permanganate and heat. If it's ozone, it's just formaldehyde. Right, it's just formaldehyde. And this will be very important. This chemistry of oxidation will become again, will show up again when we do aldehydes and ketones and carboxylic acids. Because obviously it's a way for you to make carboxylic acids. So when we ask, do you know any ways of making carboxylic acids from alkene? Oh yeah, permanganate and heat. You make a carboxylic acid. All right, we're skipping number 3. We're doing number 4. See if you can do it without looking at anybody. Create your own molecules. Go ahead. Create your own molecules.